And the way I like to think of this is, if God had a map, what would it be like? And this is really what we're trying to build. A complete model of everything indoors and outdoors that we would be able to go and see, measure, and extract, insight and meaning from it.
Welcome to another episode of the Mapscaping Podcast. My name is Daniel, and this is a podcast for the geospatial community. In just a minute, you're going to hear from Peter Atella, the CEO and founder of a company called Voxel Maps. And today on the podcast, we're talking about using voxels to build a 4D volumetric digital twin of the planet. Once you've listened to this episode and you've had a minute to digest what this might mean, what building a 4D volumetric digital twin of the planet might mean for you and what it might mean for the geospatial industry, I'd really appreciate it if you took the time to reach out to me and share your thoughts. I have a few thoughts of my own, a few things that I found particularly interesting about this episode, but I'd really like to hear what you enjoyed, what you think some of these implications might be. So you can find me on social media or search for Mapscaping or reach out to me on LinkedIn. I'm easy to find and I would love to hear from you. Hi Peter, welcome to the podcast. You're doing something incredibly interesting with voxels. In fact, you're trying to build a 4D model of the planet with voxels, and we'll get into that in just a minute. But before we do that, perhaps you could just give the listeners of an understanding of your background in geospatial.
Hi, Daniel. Great to be here. Thank you so much for allowing me to have the time to speak. So I first got started really in mapping about 17 years ago. I actually founded another company called NavMe, and NavMe was one of the very early navigation companies. So that company did embedded navigation systems for automotive, but also is one of the very first navigation apps out onto mobile phones. We used that company really to build a huge user base. We had about 30 million users on that application. And NavMe kind of transitioned over a period of time away from just being navigation into building maps. And so over a 10-year period with NavMe, we pretty much mapped the majority of the world, about 180 countries in the world, in terms of what we would call standard definition data, the kind of data that everybody uses on their mobile phones or in the cars. But about 4 years ago, we had a division of the business that was really focused on the next generation of mapping, kind of future gazing as to what that might look like. And this is where we really started to think more about maps for machines rather than necessarily maps just for humans and the requirements for that. And so really the idea was born that we should create a model of the whole planet. And that model should be volumetric. We're not just talking about a kind of a simple 3D model of meshes with no real data inside them. We wanted to measure everything in the planet. And so we took that approach, and voxels were the best way to do that.
Would you mind just describing what a voxel is for those of us who haven't heard of them before?
Yeah, absolutely. So voxels have been around for quite a while. And essentially a voxel is just a 3D pixel, a volumetric pixel. So think of it as a cube. And they've been used quite extensively in two main areas within computing. So the first are computer games. So you can render, worlds and games using voxels instead of using polygons, for example. One example of this is Minecraft. I'm sure lots of people have either played it or maybe they have children. They've probably played that game. And that's a voxel rendered world. You'll start to see actually a lot of gaming companies now moving more towards voxels or supporting voxels because there's some really nice multi-resolutional capability with voxels over polygons as well. But the other area the voxels have been used at was really in robotics. And they've been used both as a kind of an image processing technique to reduce the size of LiDAR point clouds, but also they've been used to kind of create these small maps, dynamic maps for robots. And that particular configuration is what we call a VOG, a voxel occupancy grid. So this is just kind of a 3D grid of voxels. So the typical use case was a small robot would go into a room, it would scan, it would produce this kind of basic 3D map, and it would navigate the room. What we did is we took that concept, but we applied it onto a planetary level. So the actual area of what we do is something called an MR-VOG, or a multi-resolutional voxel occupancy grid. So what we did is we took the planet and we placed a giant megavoxel, so just a giant cube, over the whole of the Earth. And then this cube is full of multi-resolutional voxels. Now, theoretically, they can be absolutely any size. For our purposes, we tend to use 8-meter voxels down to 1 centimeter voxels. And so this is like a framework, a virtual kind of construct that goes through the whole of the Earth. So this is indoor, outdoor, subterranean, through the oceans, everything. It's actually an Earth referenced, Earth fixed model. So we take this and just think of it as, if you have a standard map, a 2D map, you'd have these, the grid lines on them. This is a 3D version of that. But to start with, it's just a grid. There's no information there. Each one of the voxels has a permanent position in space and a unique address, but it's empty. So what we have to do is we validate what we call the occupancy status of a voxel. Basically, is it free space or is there something in it? So the primary way we do it, we have different sensors for doing it, but the main one really is LiDAR. So we take a LiDAR and we pass it through the environment. And as it fires the laser beams, if the laser beam goes through a voxel and it's not reflected off anything, we label this as free space. And kind of above, sort of sea level, the surface, the vast majority of actually the planet is kind of free space. But the moment that laser beam is reflected off something, we collapse down to the smallest unit of the voxel and we mark this as occupied. So what we're doing is essentially etching out the matter of the planet. We're kind of creating this very dense 3D volumetric model of everything that's there. And once we've got that in terms of the occupancy status, that kind of gives us the shape of everything. We can then do some really smart things with it as well. So we have the ability then with the voxels to layer on additional surface information on the voxel. So typically this is, data from cameras. So typically, RGB values, but it can be hyperspectral imagery. It could be radar, for example, as well. And once you place these layers on, we can then get different artificial intelligent models to look at these objects, these collections of voxels in 3D with the surface data and really start to understand what we're seeing. So we can automatically recognize features and extract meaning and attributes and measurements, importantly, to very high degrees of accuracy from this model.
Wow, there's a lot to take in. So you've built this incredible three-dimensional model. Actually, is it three-dimensional or is it four-dimensional? Do you also consider time?
Yeah, so this is the other key thing. So in the same way as we can use the AI to recognize these 3D structures, each voxel has an infinite number of time states. So as you start to do multiple passes of collecting this data, you can actually get the AI not just to recognize what's currently there in the present, but to look at those time series and to start detecting things that have changed in the past as well. So this extra dimension of time is kind of a unique feature of this kind of model.
Okay, so we've got this amazing model and an incredible amount of potential here. I'd like to ask a few more questions around the actual building blocks, the voxels themselves. Do they understand topology, or is topology built into the model? Will these voxels understand what's around them?
Yeah, so it's really built into into the model here. So really, what we're doing by measuring and kind of creating sort of etching out all of the matter is it provides this kind of wealth of information, both in terms of the shapes and the measurements, but then obviously all of the additional data. So when we then get the AI to look at these things, we're looking both at the measurement, the shape side of it, plus all of the additional information to essentially extract the information and the meaning that is required.
And earlier in the conversation, you mentioned this Earth-centered, Earth-fixed coordinate system. This, for me, at least means that this model will work indoors, outdoors, underground, below sea level, and as we travel through the atmosphere. Is that the correct way of understanding it?
Absolutely, yeah. So it really does work, across all of those different kind of use cases. Obviously, when it comes to collecting the data, some are easier than others, clearly. But the same referencing system within this global voxel occupancy grid can be used for all of those scenarios. So one of the things that I always say to people, imagine, I don't know if anybody out there has been a gamer in the past, but used to be able to play computer games, and there'd be cheat codes, and very often there'd be a cheat code which would give you like a God mode. And the way I like to think of this is, if God had a map, what would it be like? And this is really what we're trying to build. A complete model of everything indoors and outdoors that we would be able to go and see, measure, and extract, insight and meaning from it.
In just a second, I want to move off and talk about collecting data. How are you going to do that? How are you going to create this occupancy map or model of the world? First, I'd really like to know, once data is in the model, so how can we get it out again? Or is it the idea that it stays in the model, all the processing happens in the model? And I guess what I'm getting at is, if we think about OpenStreetMap, for example, it's this incredible map of the world, but we have access to it. We can pull pieces out of it, we can update it. Is that the kind of thing that you're building towards? Am I going to be able to reach into the model, slice data, and take it out of it and use it in some other sort of use case? And if there's no coordinate system, well, there is a coordinate system, but how do I sort of project that into another projection to match some of my other data?
Sure. No, great question. So the actual model itself almost becomes like a data abstraction layer. So, we collect and we store the data in voxels in this occupancy grid because we're storing and collecting absolutely everything. We're not trying to, get rid of any of the data to produce this model. But then depending on the use case, people might choose to, use it in voxels. You can do a lot of, 3D, 4D analysis directly in the platform, which might replace the need for some people to use it in different tools. But if they do need to, then it's very easy for us to export that data out in a variety of formats to be used in different tool sets. So, it's very common that the users of the data can export these things out as shape files, for example, or things like NDS for, a high definition autonomous vehicle map, or even just exporting out points. If they want to be able to use points in an area and they have a system and a platform for doing it, they can do that. But I think that once people really understand the benefits of this really what we're building is this global persistent spatial database. And once they see that, there's a lot that they can actually do within the platform, which is probably a lot more powerful than what they could probably do in existing tool sets.
I guess for me, I come back to a statement that you made earlier in the conversation where you say you're building a model for machines. And I'm thinking that machines are distributed. We think about the Internet of Things. We think about autonomous vehicles at some stage. I'm assuming anyway, they're going to need access to certain pieces of this model at some stage.
Correct. Yeah. So when I say machines, I mean that's deliberately a very broad term, and when I look at that, that's everything from, as you say, Internet of Things, different forms of AI that need to extract information from the from an environment, from a city or a different environment, but also forms of autonomy, whether that's autonomous vehicles or automated delivery robots or automated miniature robots within buildings or drones. All of these, the requirements for machines is that they have a much more detailed map. And, with this 4D model that's accurate to 1 centimeter is very different from obviously the traditional maps that we're all kind of, used to using. That doesn't mean that the data wouldn't be useful to humans. It just means that there's probably a lot of data that would be first, utilized by a machine to provide then, insight, in a human context.
So I really appreciate you walking us through the model. I realize it's a huge, complex thing, and there's a lot of stuff to talk about, but I think you've given us a really good sort of overview anyway. I'd like to sort of move off and talk about how data gets in there. A statement that really stuck out for me was that you collect absolutely everything. Could you walk me through what that process might look like of collecting absolutely everything?
The starting point for us, if we're looking at cities, for example, is really creating a mobile mapping system, which is a collection of sensors. Ultimately, it is a high accuracy lidar plus 360 camera imagery with high megapixel count plus high accuracy GPS information corrected as well. And so when you're driving those sensors through cities, they're collecting everything that everything that they can see, that the lidar is touching, that the cameras can see, is being built into a model. And so the sensors themselves on top of the vehicles will collect all the information from the sensors, fuse it together in something we call a voxel stream. And then that voxel stream is then pushed out onto our cloud, where it's merged together. It's checked obviously and cleaned and make sure there's no duplicates. But then it's merged together to create then this final product in terms of the voxels. Now that's for the city mapping side. In addition to that, we also collect from people. So there's lots of areas that cars can't go to. So there we'll use backpacks, again, similar sensors, so LiDAR plus cameras. But the difference is now people can walk, into buildings, shopping centers, parking garages, all of those kind of areas as well. And then on top of that, we also have aerial LiDAR information as well. So with some cities, we fly either helicopters or other craft above the city where we're collecting aerial LiDAR plus aerial imagery. So all of these different ways of collecting this type of data are then fused together within the voxel pipeline to create this final output and model. Now, Areas where we could expand into as well. So we're talking to a few companies about ocean mapping as well and taking some of that data, both by LiDAR, but also different types of sensors and also automated drones as well for mapping. So, we're really very much, I would say at the beginning of this, that probably the first use cases are much more around the cities. So that's where we see the fastest part of the collection. But then this is going to expand, greatly into indoor mapping and then on, into to other areas that have more kind of applications in sort of science and academia.
I want to talk about some of these use cases in just a minute, but oftentimes when we think about building a model, in general, or populating a database, there's so much data already available to us that we have the option, at least sometimes, of seeding the database, of adding stuff to it that already exists in the world, and then maybe even going out and doing our own ground truthing or building on top of the existing data. Is this an option for you? Can you seed your model with existing data sets?
We can do, and in certain areas we too, do take that on. There's some considerations around that. So not just because a data set exists, you have lidar point clouds of an area, for example, doesn't necessarily mean they're the required quality to really be able to produce the model. So if we want to really get down to this 1 centimeter or less, in terms of the resolution, the quality of that data needs to be pretty high. And also the time, when this data was collected is very important to us. So provided that we can have the input information, then we can store it. One of the things that the voxels allow for as well is kind of providing the attributes in terms of where that data came from. So we can have different providers, not just ourselves, other providers where we've ingested that data. And if the data, for example, is not sufficient resolution to get down to 1 centimeter, we have the ability, because the voxel model is this multi-resolutional model, that we can actually store course data, within the same model, but then just, visualize it at certain levels. So there's a lot of kind of flexibility in terms of, how we would ingest. But probably the most interesting thing for me comes to the indoor data space. When we're looking at, mapping cities, that's very doable. I've spent so many years mapping, different countries all over the world and building this kind of data. But when we come to do the indoor space, there's only so much we can do as a company. So, it makes sense for us to focus on commercial spaces, public areas, where there's kind of clear use cases. But there's lots of use cases here, even for the individual. But obviously, we couldn't go into everybody's homes or into their offices to map. And so that's where we're actually providing the ability for people to upload their own data into the platform that they've captured. And whether that's from something that's very high quality lidar sensor or through to an iPhone with a lidar on it, you will have the ability to do those things. So I think there'll be both a professional side of the data collection and also then almost a crowdsourced side. And the use cases might be slightly different for both types of data, but they can all exist within this model.
So I think that collecting data is one thing. You can collect a lot of data, but when we talk about using lidar and we using cameras in this case, what about identifying these objects? I mean, for me, that those seem like two separate things. Can you talk us through the process of how you identify that that's a tree or that's a car or this is a building?
Yeah, absolutely. So again, yeah, really good point. So we've got the actual collection of the data or the importing of the data, however you look at that. Then there's a pipeline for converting that data and fusing all of the different types of data together to kind of create this voxel digital twin. But then now you've got the digital twin, what do you do next? You still need to then have either a lot of people to go through that data to measure and to recognize things, or really you want to get artificial intelligence to do it. And that's what we built. So there's a platform that we built called VAMS. And essentially what this does is a collection of deep neural networks which really do full 3D semantic segmentation. So we're not talking just 2D imagery with some LiDAR points overlaid onto that. We look at the objects fully in 3D and we train and we annotate initially in 3D. So once we do that, we have incredibly high levels of recognition for these objects. So currently the platform is recognizing about 200 different objects within cities. We're doing the same kind of thing for indoor spaces, offices and malls and public locations. And we're constantly expanding then the ability of the AI to recognize these different features. And again, it's not just recognition, it's recognition, measurements, attributes, automatically, pulled out as well. So a key part of what we need to do in the future is this continuous addition of new features, new extraction, because really as the data grows, there's no other way. You need to get the AI to do the heavy lifting and provide that data and that insight. Trying to use humans to do it is just not scalable.
So just so I understand this, you're continuously populating this model, and then once the data is collected, stored, you're creating these separate AIs that are running through the model from time to time and identifying new objects or updating things. And it's simply a case of just creating a new eye for each new feature that you want to extract or identify. Is that correct?
Exactly that. So that's one of the great things, that you don't need to go and remap again. Remapping is fine, and definitely for the time-based data, it's really useful because you've already captured everything in the environment. If you need to extract a new object or feature, or you want to do measurements and count, it's just a simple case of training the AI agent to go out and do that for you. And that's a pretty quick process. Typically it will take probably around a week to train one, up to a month if it was something very, very complicated. But it's normally pretty quick to implement. And then the AI can just run, straight through the model, or a particular area that you have assigned to it, and pull back all of that information for you.
Just out of curiosity, once it identifies a feature, do all of the voxels that make up that feature, do they get tagged with specific attributes so they know that they are trees?
Exactly, they do. So all of the voxels that kind of belong to an object then have an attribute for that as well.
So it sounds like kind of messy. If you're collecting everything, for example, when I think about an urban scene, I mean, there's cars moving around, people, dogs, wind blowing leaves around. Do you collect all of that and try and filter it later on? Or is there some form of filtering that happens at that time of collection?
So no, we deliberately don't try and filter the time of collection. We for all of those objects, whether it's cars, as you say, pedestrians, cyclists, etc., those are extracted using the deep neural networks. They're not extracted using more I suppose, naive approaches in terms of KF filters, for example, just to try and detect movement and then kind of ignore that data. And implementing that is actually really useful because you just get much better quality data. It also allows you then to reconstruct scenes as well, where data might have been missing as you go through. So really the AI plays a very critical role to not obviously just recognizing the features, but also to tidy up the data and to make sure it's in its optimum state to be used.
Okay, so we've come a long way in the conversation. We've talked about building this model and how it's going to be populated, and then some of the things that are going to happen afterwards in terms of object extraction and identification. And I think you've done an amazing job of walking us through that because it's very complex. Maybe now is a great time to move on and talk about some use cases. What would be a great use case for this?
Sure. So I'll give you a couple of examples of this. So we have some projects on at the moment around creating, I suppose, what a lot of people maybe in the industry would call high definition maps for different forms of autonomous vehicle, whether that's an autonomous car or an autonomous delivery robot or some other kind of robot. So what we do here is, using the model, we extract out all of the features which are required. So things like the lane model, for example, there's semantic information that's required, so traffic signs, road signs, etc. But also we provide a localization framework. And so we have then the ability to create localization maps from voxels that then allow the robots to understand where they are in the environment and to position themselves. And again, this can work both from pure VPS, or visual positioning system, which could be camera only, all the way through to LiDAR, even to a radar-based solution as well, albeit your resolution will be a little bit less. So that's kind of one high-tech, future kind of market use case. But we've done that with some major automotives as well. Another one is actually around the implementation of things like 5G. So both kind of doing more of the standard survey stuff. So very often, when infrastructure is put in for networks, things like small cells, there needs to be an audit of the availability of space on telegraph poles or streetlights within a city. And generally speaking, whoever owns that infrastructure leases that infrastructure out there. So once they've got the availability, the telco will then look at where they can put their sensors. But that isn't just the case of, is there a spare place that we can actually put a sensor? It's also about, is it the optimum place? And so there, normally what they have to do is send somebody in to do a survey of the location, to understand what's in front of it, to work out whether this is a good location for the sensor. And this can be very expensive to do. all of this can be fully automated. So what would normally take teams of hundreds of people to go out and map the city, this level of detail, can be done with a few vehicles collecting the model, and then the AI not just recognizing the space to be able to put the sensors, but also understanding what will actually happen with the 5G signal. And we can actually model 5G signal as what we call a voxel cloud within the environment. So we can actually see how the environment impacts the propagation of those signals, both in terms of the outdoor city, but really importantly, indoors as well. So we're actually taking those models inside. So this is the first time we've ever seen anything like this, and having that 3D aspect is really powerful, but also having that 4D time-based aspect is really useful as well, to understand how this can change over a period of time, depending on where you put the sensors or depending on how that environment changes.
Talked about modeling the propagation of a 5G signal. Does that mean that, in theory anyway, I could make global weather maps as well? That I could model that kind of phenomena?
Absolutely. If the key thing is, how do you model sort of the input data? So obviously we can model the physicality, of the environment, of the shapes, of everything else. The variable data, where it's sort of not a physical thing, it depends also on the accuracy of the sensor to collect that information. So with 5G, you can do this in a relatively good way in 3D and have some useful data to plot, and then you can see how the 3D environment is actually affecting that as well. And the same would be true with weather data, depending on the type of sensors they use to collect it and how dense that information was. So obviously the quality of the data, if it's enhanced data, would be much, will result in a much better model than obviously if we don't have that, if it's just very sort of flat 2D type data.
I realize it was a bit of a jump talking from 5G signal propagation to global weather models, but I guess my point was that it sounds like there's the ability to make these really dynamic models in here. Assuming that we have access to the data needed, I guess the point for me is that opportunity is built into the model.
Absolutely. And I think, this is one of the unique things by sort of taking the planet and, converting it into this voxel grid gives you the ability to kind of discretize the environment. And then once you've got that, you can model the things that pass through that, or the things that are built there, or the things that grow there. And so those become really, really useful to look at it as volume. I mean, let's face it, we live in a truly 3D world, a volumetric world, not just a 3D world of, meshes and surfaces with no inherent data behind them. And so really we want to start looking at how we can use more volumetric data to perform these calculations. And so I can really see over a period of time that there'll be a lot more that can be added to a platform like this for many different industries and areas of research as well.
So, like the realization or the insight that we live in a 3D world, that this is not a new one, I'm sorry to say. But what do you think has sort of stopped us from doing this until now? I haven't seen many projects like this. I'm not sure if you're aware of any, but the fact that we haven't seen many of them, it's not to say there's not some others out there, but the fact we haven't seen many of them sort of suggests that there's been a roadblock for people doing this until now. What do you think that roadblock has been?
Absolutely. So really the roadblock has really been the size of the data and the ability to process, data of this magnitude. And I would say, even when we were first kind of considering this model, 4 years ago or so, it was very hard then to be able to imagine processing this amount of data at scale. And, I think that when we're kind of looking at 3D and the implementation of 3D, the vast majority of people still in this industry view 3D as, I have some 3D data and I load the file into an application and, then I can utilize it. Whereas we're saying, look, real 3D needs to be volumetric. It needs to be planet level, needs to be globally persistent. And you should be able to do calculations, to do analysis on the whole data set. But to do that, you need an incredible amount of storage and also processing power, both of which are totally feasible now. Potentially sort of 3 years ago weren't really feasible.
Do you think this is could this potentially be the last data model that we need in terms of geospatial? Or is there use cases out there where this is just not going to work, where this is not the right answer?
I mean, I'm sure there's always, use cases where, voxels aren't necessarily the optimum way to do things. I still think, though, that the fact that voxels work as a data abstraction layer, so allow you to collect and store everything, but then export out into different formats, is useful. again, one of the issues with voxels is just the size of them in terms of the amount of data you're having to store. Although there's lots of clever ways to optimize that. So in some use cases, for example, if I spoke before about building the map for autonomous vehicles and the maps for drones, they don't need a full copy of the voxel map, to process. So what they actually have is a subset, kind of a sub map, which is kind of created from it, which is then just much more useful for them in terms of their processing power. So I think that there's a huge value to utilizing the voxel approach. I think we're just really at the beginning stages of this. I think volumetric is going to become such a huge thing, particularly as well with the gaming industry starting to really get behind this as well. And really, the nice thing with this multi-resolutional approach is you don't have a limit on the resolution. There's no reason why we couldn't do 1 millimeter, voxels. Theoretically, it's possible, but there are constraints in terms of processing time and the quality of sensors that are available to try and create this data. So I think you've got a lot of future proofing built into a model like this.
So creative destruction is the idea that when a new technology shows up, it makes an existing technology redundant. And this we see this all the time in the geospatial industry, in the tech industry at large. What are you going to replace here with this model? What technology is this model going to make redundant?
I think there's a lot of analysis that's done in geospatial, which is really done in a 2D way for simplicity and ease. And actually, looking at it in 3D would be much more useful. So, just standard concepts of having layers of relatively basic data, overlaid onto a 2 or 2.5D map. I think a lot of that will be replaced, and there'll be easier ways of doing things. And even to the point that the data that you're kind of building here really becomes this spatial database, which you'll be able to search for information. So kind of even just sort of plotting areas and extracting manually as layers in the old way of doing things will probably be replaced with some form of intelligent search that will be geospatial and volumetric and be able to pull this data back. So I'd see kind of those kind of traditional geospatial tools, the big tools that the majority of people use. I would say a good 80 to maybe 90% of those kind of functionality could be replaced or improved in a 3D model.
I can see a ton of crossover here when I think about what you're building, this volumetric model of the world, and something like augmented reality, for example, because augmented reality seems to have a bit of a problem in terms of location. But if we used your model, if we located ourselves on your model of the world, it wouldn't stop. There'd be this seamless transition between inside and outside, and we'd have a volumetric world to interact with. Has anybody approached you and said, hey, this is going to be perfect for our augmented reality ideas?
Yes, I can't say who exactly just because of confidentiality reasons, but we have models already working for VR and for AR. So virtual reality is more on the traditional kind of explore the data, survey, virtual surveys, those kind of things is the VR application. The AR applications are particularly interesting, both in terms of positioning of content, but also starting to look at new consumer models, consumer models whereby you might want to create a structure which would map your internal spaces and which would be secured. So they'd be private to you. You'd have to give permission to access them. But then you could choose different services which would allow different businesses into to essentially to sell or to supply services to you. So things can be virtual surveys, virtual carpet installations where they can actually have a look at the the inside of your house and measure up without even having to to be there, through to augmented reality around different objects that you might want to have in your house as well. So that kind of use case is really being put together, and we have a few demos. And interestingly, that AR piece is not dissimilar to some of the robotics stuff that we talked about in terms of localization as well. So very similar kind of technologies in the visual positioning systems are used really to localize data to this really high degree of accuracy.
So this is a really big idea, and it's a really, really big idea. What makes you think that you're the right person to bring this idea to the world?
I suppose I don't even really sort of think about it in that way. I think my background in terms of what I've been doing for 17 years and building maps of the world has kind of stood me in good stead for thinking about this. But the reality is that we build our company builds maps at at huge scale for ourselves and for our clients. So we're collecting millions of kilometers of data, every year around the planet of building this kind of mapping. So, we know what we're doing. We've been doing this for a long time and building it up. That being said, mapping the entire planet is a huge ask. Even companies like Google, they really would, struggle just doing it entirely by themselves in terms of all of the different types of data that can be collected. So really, I think what we need to do is really expand out the collection. So what's so important to us is not just the collection with our own sensors and our own teams, but also empowering then the crowd or other companies or other organizations to be able to collect data and contribute data as well to the project. So we'll be opening up later on this year a platform which will be online that will allow people to do that. And that's quite exciting for us.
What would you say to someone else out there in the geospatial community that has an equally big idea? Should they just go for it? Or what do you think needs to be in place first before you start, implementing?
I think it very much depends on what they're trying to do and what they're trying to achieve. I think there's very good technical solutions to a lot of problems that are out there. But I think, you've kind of got to look a little bit further down the line in terms of who's going to be using the data and what are their needs, wants, and problems. And that can include future gazing. You can see that there are potential problems in the future that will need this. If we think about it, at the moment, everything's being virtualized and we still don't have a full model of the whole of the world. That's inevitable. That's going to happen. And, we very much believe, that we're going to be one of the key, players in this to enable it. So I think if they've got a big idea and they understand where they're taking it, then they should go for it. If it's just an idea which might, be hard to get buy-in, for people or excite people in a way, then, that comes down to really, the execution. What's the plan for kind of getting people on board or getting the data on board and doing it?
Peter, I really want to thank you for coming along today and teaching us all a little bit more about what the future might look like in terms of mapping. It's been a really enjoyable and inspirational conversation. So thank you very much. Where can people go if they want to reach out to you or if they want to continue this conversation?
No problem. Thank you so much as well, Daniel. So people can just visit our website, voxelmaps.com, and I'd be super, interested to hear from people. So, do feel free to reach out to us there and start a conversation.
Thanks again, Peter. It's been really inspirational.
Thank you. Take care.
I really hope you enjoyed that episode. There is a lot to take in. This is the second or third time that I've listened to it before I record these intros and outros. And I am still walking around the house, wondering if I've completely understood the concept and some of the potential implications of building a model like this, what you can use it for. There was a few new acronyms for me during the conversation. One of them was VOGS. So VOGS are voxel occupancy grids. Another acronym that's worth noting here is the multi-resolution VOGs. So MR VOG, Mr. VOG, if you will. Possibly a distant relation to Mr. Sid, but don't quote me on that. And that's it from me. That's it for another episode of the Mapscaping podcast. Thank you so much for tuning in again this week. It's much appreciated. If you are a long-time listener and subscriber to this podcast and you are interested in supporting it, the best thing you can possibly do is just share it with a friend. I would really appreciate that. As always, you're more than welcome to reach out to me. I am active on Twitter at Mapscaping and LinkedIn. Just search for host of Mapscaping podcast and you'll find me there. There'll also be a link in the show notes. Okay, that's it from me. We'll talk again next week. Bye.